Alright, so finally today we are going to prove that every symmetric group Sn where n is at least 5 is non-solvable. Now in order to get to that result, we are going to need this lemma. This lemma states that if G is our symmetric group Sn where n is at least 5, then these subgroups Gk all contain every 3 cycle of Sn, regardless of what this positive integer k is. So let's first see this proof. In the beginning of this proof, we are going to use a fact about any group. Let n be a normal subgroup of an arbitrary group that means this G is not this G, but this G is any group whose normal subgroup is n. Then the commutator subgroup of n prime, is also normal in G. We won't prove this remark itself right now. It is one of the exercises. So we will solve it when we solve all the exercises. We are, however, going to use this fact in this proof. And for this, see exercise 5. Alright, so now we start the actual proof. In this proof, now we are going to start off by taking a normal subgroup n of G. This time, however, G is our Sn, which contains all the 3 cycles of Sn. Let n be a normal subgroup of G equal to Sn, where n is at least 5, that contains every 3 cycle of Sn. Then in particular, n will also contain these 2 specific 3 cycles. Then in particular, n contains this 3 cycle 1, 2, 3 and this 3 cycle B 1, 4, 5. Note that we have been able to choose these 3 cycles because n is at least 5. There are at least 5 symbols available to us on which we can apply these permutations of Sn. Now, because we have A and B in n, the commutator formed by these 2 elements, that is A inverse, B inverse, AB, will by definition be an element of n prime, that is the commutator subgroup of n. Now, A inverse, B inverse, AB belongs to n prime. Let us now calculate this element because we know what A and B are exactly. So A is 1, 2, 3. In order to write its inverse, you can just use the reverse order. Well, let me just, I suddenly got confused. Is it really the reversed order? I mean, if I write 3, 2, 1, A sends 1 to 2, so its inverse should send 2 to 1. Yes, yes, yeah, it's okay. Similarly, B inverse is 5, 4, 1, then 1, 2, 3, followed by 1, 4, 5. So let's now calculate this product. First of all, let us see where 1 will go. This permutation sends 1 to 3. This one then doesn't change 3 because it does not have 3. This one then sends 3 back to 1. That means we are back to 1. And this one then sends 1 to 4. That means ultimately 1 goes to 4. Next we see where 4 goes. This one doesn't change 4. This one sends 4 to 1. This one then sends 1 to 2. And this one then doesn't change 2. That means 4 goes to 2. And then what happens to 2? 2 goes to 1, 1 goes to 5, 5 is unchanged by this one, and then this one sends 5 back to 1. That means it sends 5 to 1. So 2 goes back to 1. Okay, so that's it. So this is also a 3 cycle. Hence, this belongs to n prime. Now by the first remark, because our n is normal, n prime is normal in G, since n prime is normal in G, we have pi inverse 1, 4, 2 pi belonging to n prime. For all pi in G, which is Sn. Okay, do not confuse this pi with the irrational number pi. This is a permutation. If you want, you can just simply write p or any other letter. All right. Now, for any 3 distinct integers I1, I2 and I3 in the, well, I should not perhaps say integers because these are just symbols, in the set of available symbols on which the group Sn acts. For any 3 such distinct symbols, that means these are all different from one another, choose a permutation pi in Sn, which is our G, such that the pi image of 1 is I1, Okay, so we are going to go in this order. The pi image of 4 is I2 and the pi image of 2 is I3. If we have this, then it's pretty easy to see that this product will be the 3 cycle I1, I2, I3. In order to see how, there are two ways. You can argue like this, going through a detailed calculation, or just from these equations itself it follows that this has to be this 3 cycle. And for that you go back to that section on group theory where we investigated the conjugacy relation in the symmetric groups Sn. There actually we learned how to calculate conjugates of cycles, in fact conjugates of permutations, and there in fact we also figured out that two permutations are conjugate if and only if they have the same cycle structure or the same cycle, similar cycle decompositions. So there if you go, there you will see how one can immediately figure out that this has to be this. So I1, I2, I3 belongs to n prime. However, this is just any cycle in Sn. Any 3 cycle in Sn. So we have proved that n prime contains all the 3 cycles in Sn. In other words, n prime contains all the three cycles in Sn. So what have we proved actually? We have proved that if a normal subgroup N of Sn contains all the 3 cycles, then its commutator subgroup also contains all the 3 cycles. Now, we are going to take a special value of n. Value of n means in place of n, we are going to take a special normal subgroup of G or Sn, namely Sn itself. Taking n equal to G, which is, first of all, this n of course is normal in G because G is normal in itself, and contains all the three cycles in Sn. We conclude by what we have done so far that n prime, which is G prime, contains all the three cycles in Sn. Now G prime contains all the three cycles in Sn and G prime is normal in Sn. So in the next step, you can take G prime in place of n. Similarly, since G prime is normal in Sn or normal in G, same thing, we have that the commutator subgroup of G prime also contains all the 3 cycles, which by definition is G superscript 2. We have that G2 contains all the 3 cycles in Sn. Now G2 is also normal in Sn, so you see the pattern. G2 is normal in Sn and now it contains all the 3 cycles. So its own commutator subgroup, which is G3, will also contain all the 3 cycles. So no, should not write proceeding, but continuing. Like this, we conclude that Gk contains all the 3 cycles in Sn for all positive integers k, and that's what we wanted to prove. Now with the help of this lemma, we are finally going to prove this next theorem. And that theorem is simply this: Sn is not solvable for all n greater than or equal to 5. Let us now recall the equivalent condition for solvability of a group. I mean, the definition of course involves a chain of subgroups and all those things, but in the previous video we proved that we can come up with a simple equivalent condition, which was that one of those groups Gk has to be trivial. That is the condition for solvability. That is equivalent to the condition for solvability. By the previous lemma, because we are considering symmetric groups where n is at least 5, Snk is, or rather contains, all the three cycles in Sn for all positive integers k. But then definitely Snk cannot be trivial for any k, because the trivial group of course does not contain all the three cycles. It in fact contains none. So Snk is non-trivial for all positive integers k, and so no Snk is trivial. It can be trivial, and that's why, let me recall what was that equivalent condition for solvability. Lemma 571. Hence by lemma 571 Sn is not solvable. Okay, so we have proved what we were claiming all along, that for such n's where n is at least 5, Sn is not solvable. Now using this fact and some other things, we will be able to prove that result, that no general polynomial equation whose degree is at least 5 is solvable by radicals. That, however, we won't go into today. It will be dealt with in the next video, next Galois theory video. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.